so in the first part, we talked about various kinds of partitions, right? And how to study them, right? All these tools, partition functions, Young diagrams. And so those are pretty effective tools in proving theorems. So what happens next? We need to decide. So basically, the rest of the course will be, I will give you some paper or a book or several of those to read and process, and then we'll be studying them with you together. And then sort of the idea is to get you to the cutting edge of modern science, whatever it is, in that field, right? In that subfield. So at least you would understand what people are talking about in those papers. And yeah, so basically at some point, it doesn't have to be today, but maybe over the course of this week, you just send me send me your suggestions, like what kind of stuff you want to do. So we'll list it today. I'll make some suggestions now, but maybe at this moment, some of you already have some ideas. Do you guys understand what they want to do? Like, so we talked about partitions a little bit, right? And remember, I told you that, well, to prove various theorems, for example, here, like you need, for example, to prove this theorem about asymptotical behavior of the partition with large n. Well, formula like this, right? So they require knowledge of complex analysis, integrals in complex plane. So that could be one direction. We can study that in more detail, right? So first we need to study the basics of complex analysis, and then we would use those complex integrals for proofs. If analytics is something that you like, or we can have some more combinatorial applications. As you can see, those Young diagrams are a very powerful tool in, well, proving theorems as well, right? You can explain it to an elementary school kid, right? Or how to move diagrams. So we're going to prove one today. So after we're done checking homework, I'll show you a cool theorem, which in terms of partition functions, is one big expression equals another big expression. In terms of diagrams, it's just, moving the blocks around, or just even looking at the diagram, right? So it's also pretty powerful. Or we can look at such physics geometry applications of partitions where they are, right? So how sums over partitions arise in various kinds of counting problems in geometry, right? So for example, you may ask yourself, well, I'm going to say much more about everything here. I just sort of making a kind of an announcement. So say you have some space, and then there's a curve inside the space. So everything can be complex. So it's actually a complex curve, right? And then you, for example, asking yourself, like, how many times it intersects with itself, or how many times it intersects with any other curve, right? And in order to answer those kinds of questions and their generalizations, people study certain moduli spaces of curves. So it's a space of parameters which determine these geometric objects. And then you study various properties of this moduli space. So usually it's a very complicated dimensional space, non-compact, but with some tricks, you can sort of tame them. You can understand how to integrate over those spaces and so on. And typically, result of this integral is a sum over partitions. Yeah. So and very often it's not just those partitions, but so-called plane partitions. So imagine you're looking at the corner of a room, right? So this is floor, and this is, well, wall on the right, and this is wall on the left, right? And then what you're doing, you're taking cubes and then putting them in the corner, right? You're staking them one towards another. It's kind of painful to draw, but I hope you understand what I'm talking about, right? So there's a cube here, and then you could put another cube there, and you can put cubes on top, etc. So you can, so the only rule is that every slice, right? Every slice in, well, either in this direction or in that direction is a Young diagram, right? Only in one of the directions, it turns out to be kind of mirror reflected. So you're not allowed to pile up any mountains, which are sort of, on the inside, on the interior of the room. So yeah, and then you're just looking from on this thing from the top and just counting how many. Now it's called plane partition, right? Well, because well, that's what it is, right? It's essentially you're looking at the corner, and then you would put in. You can think of it like this, right? So you have those cells, right? And then you put in numbers, right? So for example, 7, 6, 5, 4, 2, 1. So which means that here we have 7 cubes, here we have 6, 5. Yeah, so you can see this is a Young diagram. So if you kind of look at this from here, so this will be 6, 2. Right, and then this will be 7, 4, 1, and so on. So it's a 3-dimensional structure, right? It's called plane partition. There is a partition function. So I'm going to write down the formula for partition function, and I hope you'll get amused. So remember the Euler formula for the partition function. What was it, right? So P of n, right? So the generating function sum P of n z to the n goes from 1 to infinity, was equal to product 1 over 1 minus z to the n. Like this, right? We know this. We prove this. It's you are supposed to know this at this point. But right, that's what the first kind of 3 lectures with all these moving blocks and pentagonal numbers were about. Now, so this is for normal for partitions like this, for so-called for integer partitions. Or if you like, you can call them 1-dimensional partitions, because it's really your stacking blocks in one direction. Okay. Now, you can ask yourselves, well, is there a function that counts these guys, that counts plane partitions? And I'm going to write the formula next to it, and you will be amused by so it's plane partitions, PL P of n, z to the n from 1 to infinity. And you just watch, guys. It's so beautiful. So it's minus z to the n, everything to the n. And that's it. Right? So it's just, you just simply exponentiate every parenthesis and claim that this counts plane partitions. So we can talk about this. Proof, as you may imagine, is much more complicated. So it requires certain technology, which we can discuss. Like there are, I think I'm aware of maybe 3 or 4 different proofs of this fact. And then sort of learning each of those proofs will be, sort of a story on its own. Yeah. So by the way, our hero from the movie, this Piercy McMahon, that's arrogant British professor, right? This formula bears his name, so it's called the McMahon formula. McMahon. Well, and then you can ask yourself, can you go beyond that, right? So if these are 2D partitions, are there 3D partitions? Right, so which means that you cannot probably draw this anymore. Well, anywhere you should visualize them, right? It's basically you have space, right? So why I'm writing this so small here? Let me copy it. Yeah. Since I started talking about it, so this will be kind of future directions. Yeah, so this is a right. So we have this McMahon formula, and then you can also, yes, we have 1D partitions. This is Euler formula. 2D partitions McMahon. And you can ask, can you go beyond, right? Is there a sort of systematic study of partitions in higher dimensions, right? And by this I mean, so think of, so for example, in 3 dimensions, so say you should probably think of it like this, right? So you have a cube in space, which in fact should be an unlimited size, right? And then you would you know, sort of dissect this cube into cells, right? And then in every cell you would write a number. So, you know, 10, 8, 5, right? Such that every kind of slice in this direction, pretty much every slice in each of the 3 planes in 3D space is a plane partition, right? So yeah, you cannot draw this in 3 dimensions, right? It's like it's in a sense it's a 4-dimensional object, right? So integer partition, if you like, the Young diagram for integer partition is 2-dimensional. Young diagram for plane partitions is 3-dimensional, and what to be Young diagram for solid partitions they're called, right? So 3D partitions or solid partitions. So these are called integer partitions. These are plane partitions. And these are solid partitions. So you can ask yourself, well, can you write a magic formula like this, or, you know, other formulas? Like, it's not only things that you can count. As you remember, so here in integer partitions, we counted various kinds of things, right? We counted odd distinct at the same time, etc., right? And they all had their own partition functions, and they were interested in on their own right. So, and you can ask yourself what happens here. So it turns out that the answer is yes, is positive in all these 3 cases, but then starting from higher dimensions, you can prove that it's not possible. So it is not possible to write a function like that. Yeah, there are various reasons. So which kind of become apparent. Well, some of them become apparent once you study this. Once you study solid partitions. So yeah, so that's kind of another direction, sort of potential way to go. Yeah. Right. So that's that. So yeah. So do you guys have any ideas right now, or what they say? Have you thought about? Asked me to think about this last time. Do you have any preferences at the moment? It's okay if it's not, but I just want to check.
I had an idea that I thought of last week. Basically, like I was looking at integers using like Riemann sums.
Mm-hmm.
So, like I'll show you 1 second.
Okay.
So like using the context of Riemann integrals and Riemann sums, you could take like subintervals and break them apart using different partitions. So like incorporating calculus into the like partitions.
Good. So you're interested more into this calculus kind of stuff, right? And then potentially complex analysis, right? With those complex integrals. Would that be interesting for you? Great.
Yes.
Yeah. Good. So yeah. So we can start working on that. Yeah. But if you decide to change your mind, let me know. Yeah. So yeah. Right. So there's also the potential directions. We can write down them here. So here this is so that was kind of the big. Let's just call it combinatorics, although it's much more than that. Combinatorics of partitions. So a second kind of big topic would be yeah, so analysis, kind of analysis, kind of applications of partitions in analysis, or vice versa, sort of applications of analysis in partitions, I would say. So we still want to study those partitions. Let me just start analysis in partitions. And here in particular, so what Emily said, say complex integrals. Well, she said just Riemann integrals, but let's just write them both, right? So Riemann integrals, complex integrals, and connections to partitions. Right, and then also sort of applications of analysis in proofs, right? So using analysis in proofs. In proofs of combinatorial theorems. Yeah. So this will require, we can already put some notes here. So there'll be some requirements. No, not requirement, it's a strong word. So let's put a to-do list. Kind of what we need to learn. There's a to-do list here, of course, right? So all of those, I mean, it will require stuff, to know something beyond, the AP, everything, right? So it's, but we can do it. I mean, it's, if you only focus on this thing, it's possible. So here we need to learn complex analysis. Right. So, for example, I'll give you an example. So if you have a function, complex function, 1 over z. So if z is a complex number, right? So everybody knows what complex number is, right? So you have a plane, right? And then a point x, y, you can associate to a complex number z, which is x plus I, y, right? I squared is equal to -1. And you can add those numbers and multiply and even divide if it's a non-zero number. So this set of complex numbers, it forms an algebraic field where you can introduce operations of multiplication, addition, and inverse, right? So the inverse. So if you can do it, it's called a field, right? So, there's a group, there's a ring, and then there's a field. Yeah, so complex numbers are, it's a great tool. So for example, every polynomial equation has a solution, or in fact, as many solutions as the degree of the polynomial, if you count with multiplicities. So fun fact about this, now say you have this function f of z, and you want to integrate this function over the path. So probably you may have heard that not only can integrate over a line, like like normal Riemann integral from a to b f of x dx, but you can also integrate over curves. So the way you do it, you parameterize the curve by sort of so how to integrate over a curve in this Riemann sense, right? So you still do your integral from a to b, but then you compose it with the function phi of t. So say if this parameter t that runs through the segment, right? So if t is between a and b, and then so this is it's phi of a, phi of b, and then here is an image of some function phi of t. Then integral, let's call this curve gamma. So integral of a gamma of function f is equal to integral from a to b, f of phi of t, and then there's a derivative, right? Because there's a differential phi prime of t dt. Does that make sense? So when the parameter t runs from a to b, its image under this map runs through this piece of the curve. Are you familiar with Riemann integral? So what does integral from a to b means? I see some. Is everybody familiar? Oh, Eunice is sitting in mask. Are you with other people too, or just or is it the Zoom effect that you have in a mask? Okay, probably some in some public place. Yeah, that's okay. Yeah. So yeah, well, okay. If capital F is the antiderivative, right? So of f, so it's a function whose derivative is equal to f. Then what is this thing equal to? Let's check your sanity check. It's the main theorem of calculus, right? Newton-Leibniz formula. I
That
see
would be
choosing
equal
ladder.
to,
Yeah, go ahead, Kyle.
yeah, that would be capital F of B minus capital F of A.
Yeah, that's right. So it's the difference of this antiderivative at end points, right? And then you can expect the same thing from in this case, right? Now, so for example, if you believe this answer, I mean, if you believe kind of the analog of this answer here, so, and now you can ask yourself, what happens if you make this point and bring it all the way here? So what if it's a closed loop, right? So naively, the answer should be 0, right? Because it's the value of the antiderivative at the point minus itself, right? But that assumes that, okay, so just so let's say it's equal to question mark. Is it equal to f of phi of b minus f of phi of a? In the sense of is this true? Right now, why can't this be true? So yes, okay. So this is of course true. I'm sorry about that. Yeah, so this is of course true. But then, well, what happens if you have, so this function not only is defined not only on this curve, right, but it's also defined like everywhere else, right? So say this is a curve, you know, it can be self-intersecting, and then come back again. So say this is curve gamma in the complex plane, and then this is, you know, phi of a equals phi of b. Now, if a and b is at the same point, this is 0. We believe we can ask, is it equal to 0? Right, and now think of function f as a function that not only kind of is defined on this curve, but defined everywhere on a complex plane, like function 1 over z. So where z is a complex number, so it's defined everywhere unless z is equal to 0. So let's see what it is, right? So it's 1 over x plus iy. You probably know how to extract real and imaginary part from here. What do we need to do? So what's the real part of this function? What's the imaginary part of this function? Or like, you know, that's the same with numbers, right? So for example, where in the complex plane is point, you know, 1 over 1 plus I. Does anybody know? So you want to represent every function, every complex number, you can write it as a plus, well, a plus ib, right? A is called real part of z because it's just, you know, the x coordinate, and b is called the imaginary part of z. There's a trick that we need to implement, which is pretty standard. So once I in the denominator, you need to do something about it. Can we lift it up?
You can use the conjugate.
Yeah, precisely. You multiply by a complex conjugate, which means you multiply by 1 minus I, 1 plus I, 1 minus I, right? And then what we'll get in the denominator? Let's multiply 1 plus I times 1 minus I.
2.
Yeah, that's right. So it's 1 minus 1, right? So yeah, which means it's 1/2 minus I/2. So the same thing you can do with this function. So tell me what this will be equal to. What is 1 over x plus iy? So we need to multiply by conjugate, right? So it's x minus iy divided by x squared, x squared minus y squared, right? Sorry, plus y squared, yeah. Because you multiply by x minus iy, and then you get the x plus, let's write it down. In fact, let's not save space, let's move it elsewhere. So x minus iy. So I just multiply, divide by the same function. So here in the denominator we have x squared minus iyx plus iyx, and then plus y squared, right? Plus because it's I squared is -1, and then there's another -1 from this minus in parentheses. So this is x over x squared plus y squared minus, well, let's leave it like this, plus minus y over x squared plus y squared times I. Yeah, so this is the real part of f. This is the imaginary part of f. So you can see, yeah, f. So it's defined everywhere in the complex plane. And now you can ask yourself, what if you integrate this function 1 over z over this path here? Over the unit circle around the origin. So you integrate, let's call it so gamma 1 over z dz. So it's a closed loop. It starts and ends at the same point, say this one. So does anybody know what the answer is? Maybe hard.
Can you repeat the question?
What is this integral equal to? So we are integrating in this sense, right? In the sense of this path integral of a path. Function 1 over z, which is given by this expression, over this loop. In fact, let's do even more. Let's do something more interesting. Let's put any integer power here, 1 over z to the n. And we can ask ourselves how the answer will be different for different n. I mean, if you haven't done it, of course, you won't be able to tell. Don't kill yourself. It's okay. So we'll do it two ways. So first, we'll do the brute force calculation, and then we'll essentially write the answer based on a certain theorem and complex analysis, which is in fact is the most powerful theorem which is used here. So, and that theorem will be needed to understand this part. So understand how there's a main formula in complex analysis, which I'm going to tell you, and which does magic, as you can see. So if you looked at those kind of expressions, you can understand this is pretty messy, right? So you need to find the right parameterization, you need to compute all these derivatives, and then you need to be worried whether you can actually do the integral. As I'm sure you know, not every function is integrable, right? So if you write a function out of blue, it probably does not have an antiderivative, right? And by the way, it's not just, so you ask your computer, your favorite programs in Mathematica or Maple, do this integral, and it says, I'm sorry, right? So it says she's sorry, not because it does not know what to do, but because it knows for sure that the answer doesn't exist. So you can prove a theorem which would definitively tell you whether the antiderivative for a given function of one variable exists or not. It's a certain elimination algorithm. Yeah, of any elementary function. Elementary means sine, cosine, exponential, polynomial, and the combinations thereof. So you give some crazy function, e to the x squared log x plus some big fraction, and ask to do the integral. So unless a miracle happens, it's not possible. But it is possible to do a complex integral with pretty much everything, provided that the function is differentiable. Yeah. So okay. So let's do this here. So now, before in order to do this, let's recall another. Well, recall, or let me tell you for the first time. So z is equal to x plus iy is not the only presentation of a complex number. So the other one is the exponential presentation, is e to the I phi, right, where phi is absolute value. Yeah, so this is the so-called polar coordinate presentation, right? So let's do that. So say you have a point here, z, which is x plus iy, right? So this is x, this is y. And this is absolute value of z, which is just the distance from the origin to the point. So of course, the Pythagorean Theorem, it's square root of x squared plus y squared. We can call it it's the magnitude or absolute value of complex number. It is also, as we've seen, it's equal to z multiplied by the conjugate z. So conjugate z, I remind you. So if z is this, then conjugate z is x minus iy. It's called a complex conjugate. Of z. Yeah, I think it's good that we're spending time on this because essentially everybody needs to know this at some point as square root. Right. So, and then this phi is this angle here. So if you like, tangent phi is y divided by z, y divided by x. Well, why is this true? So there is a formula in, oops, what happened? Oh, I hope my annotation did not. Oh, it's all here. Yeah, it's nice that notability saves everything. Oh, guys, by the way, so do you guys have immediate access to the videos, or do I need to upload them by hand? So after we're done, can you, like, when you log into the Schoology portal, do you see the videos or not? Because, or do I need to like manually send you the link?
I think you have to manually post them.
Yeah, okay, good. Yeah, thank you for letting me know. Somehow I thought it's been taken care of by the admins, but apparently it's not the case. Okay. Yeah, so yeah, I think I uploaded them on YouTube, like the general lectures, and I posted the link, right? So first for 4 lectures, I think I cut some material. Like, I had to cut the movie clip part because I would have issues with copyright. Yeah. So probably done this unlisted videos, but okay. So maybe somebody can tell me, so why this presentation is legit? So why this is equal to that?
Maybe it's like Euler formula.
Right, good. So which says that e to the I phi is equal to what?
Cosine phi plus I sine phi.
Good. So
Yeah.
there are various ways to prove it, right? So one of the probably most straightforward is to do the Taylor series, right? So the Taylor expansion of the exponential gives you all powers, cosine gives you even powers, and sine gives you odd powers, and they just add up together. Yeah. So and then just to make sure that yeah, good. So so you can write this down if you're going to continue here. So this is equal to, yeah, absolute value of z cosine phi plus I absolute value of z sine phi, and from elementary trigonometry, right? So this is x and this is y. Okay. So in order to parameterize the points on this circle, absolute value of z is equal to 1, right? It's the unit circle. So all of those points have all these complex numbers. They have, you can parameterize them as just this phase, right? So a point here is e to the I phi. Right? So absolute value of z is equal to 1 here. So let's write it down. So you have excuse me. So yes, so z is equal to e to the I phi, right? So phi takes values between 0 and 2 pi, of course, to make a full rotation. And then, well, what is z to the n? Just z to the n, I n phi. So in order to set up this integral, what would do? We'll integrate from 0 to 2 pi. Yeah, so if z is this, and then and dz, the differential, what is dz? We just need to differentiate this function. So, and think of I as just a coefficient. It works the same way as 2 or 3 or. So d by differential of e to the I phi. How to express dz in terms of d phi? What is it?
Would it just be I e to the
Yes, I e to the I phi d phi, right? Because you just do derivative of the exponential is exponential, and then there's a coefficient in the power, so you just pull it out, okay, and then since z is e to the I phi, you can also write it as I z d phi, right? So we're ready to write down the integral. So it's equal to, so dz is I z d phi. Oh, z. Okay, let's write it down. Okay, probably we're not going to use the last part here. So it's I e to the I phi d phi divided by e to the I n phi. Okay, so far so good. And then, okay, I'm going to continue. Okay, let me move it here. It's so nice to write on this thing. You can just move things around. Maybe also move it here too, as a part of the preparation. So we have what? We have this is equal to, you can just simplify integral from 0 to 2 pi I e to the minus I n minus 1 phi d phi. Good. So now you should be able to do the integral. So as Kyle told us, it's a Riemann integral, right? So with the I, but okay, still it's a Riemann integral. So what is this integral equal to? Let's calculate. So we need to calculate the antiderivative, and we need to calculate the difference of this antiderivative at 0 and 2 pi.
Professor,
Yes.
I have a question. When we are calculating integral that's involving the complex number, should
It
we
behaves as just any
treat
coefficient.
it like
So,
a constant or something? Treat I as a constant or
yeah, we treat I as a constant. Yeah, exactly. So
Okay.
that's what a field means. Like I is just another same constant as 1 or square root of 2 or 3. Yeah, so it behaves the same way as other coefficients in well in this calculus theorems for the Riemann integrals. Yeah, so exponential is a very easy function to integrate, right? And we'll look at the answer at different values of n. So here, n is an integer. But let's try to write down the antiderivative first, and then yeah. Yes. So we need a function derivative of which is equal to this integrand here. Zero, do you calculate? And so what's integral e to the alpha x dx, right? It's 1 over alpha e to the alpha x plus a constant, right? So integral of this, so I is the coefficient. You can put it up front, and then it will be just 1 over minus I n minus 1 e to the, like this, right? And I'm not writing a constant because we need to do this substitution here. Right, you can cancel things like negative I, but so what is this equal to? So we just need to substitute. So we need to plug in 2 pi, and then you need to plug in 0 and subtract one from another. So what's e of 2 pi I times, say, n, where n is an integer? So look at this formula, right? So complex exponential is a sum of sine and cosine, right? So what is cosine of 2 pi n, where n is an integer?
One.
That's right. So it's equal to 1. And how about sine of 2 pi n?
0.
0. Good. So because it's a periodic function, right? With period to pi, that's what it means. Okay, so given that fact, what is the answer? So we need to remember, we need to substitute 2 pi and then substitute 0 and subtract one from the other.
Well, the answer is just 0 because 2 pi and 0 are always like the same angle when it's multiplied by an integer n. So
okay, good. So it is equal to 0 most of the time, but is it 0 for every value of little n? Is there anything special when little n is equal to 1? So clearly, when little n is equal to 1, this formula doesn't make sense, right? So we need to go back here. So what is the value of the integral when little n is equal to 1? So when n is not equal to 1, so that when this denominator here is non-singular, right? The answer is indeed 0 just because of periodicity of trigonometric functions. Is that part clear? Yeah, so just it's simply because sine 2 pi n is 0 and cosine 2 pi n is 1 for every n. Now, but let's just plug in here n is equal to 0, right? So n is equal to 0, which means the exponential is gone, right? It's equal to 1. So what's the answer then?
then that answer would be 2 pi I.
Yep, that's right. 2 pi I when n is equal to 1. And this is, well, it's a really big deal, right? So you see, somehow n is equal to 1 is so this function 1 over z, the first power, is a very special case, right? So as you do this kind of integral around the origin, so it has a pole, right? It has a pole at the origins. It's in other words, it's not defined, right? So this function 1 over z takes your complex plane minus the origin, right? And sends it into the complex plane. So because origin is not part of the domain, you cannot simply contract the circle to a point, right? You cannot. So we'll talk about contraction in a second, but yeah. So the fact that there's a puncture there, right? It's like a complex plane which is not defined at this point makes it possible to have this answer. But you can ask yourself, okay, 1 over z to the any power n has a singularity over here, right? But nevertheless, if you do this integral for a pole of any higher degree, say 2, 3, or 100, the integral is still equal to 0. So this 1 over z is a very special case. Okay. Now, so that's kind of, it's the first part of the So I'll make a statement in two parts. So part one is this, and then part two, let's just start as a theorem. Is that if f of z is differentiable, let's write this on the U, which is an open subset of C. So think of open subset as just some set in a plane without the boundary. Right. So for example, open disk is set of Z, which is less or equal than 1. Right? So it's Z in a complex plane such that there's a sort of disk, open disk centered at 0 with radius 1. Right. So if f is differentiable on every point in Z, and this is not the case here, right? So if you take some open disk containing the origin, f, this function is not differentiable at the origin. So this will be the previous example will not follow the theorem. Then integral of f over gamma for any gamma, which is a closed path in U, is equal to 0. Yeah. So if there are no singularities, then you can, every closed path you can contract to 0, right? Essentially be, yeah. So if in the previous example you would have, integrated over something, any closed path, doesn't have to be any regular shape. It can be so something like this. And if you integrate function 1 over z, integral will be 0, and you don't have to worry about the complexity of this path. You don't need to find some complicated way of parameterizing the curve, doing the integral. All this is unnecessary. So in a sense, the theorem does magic for you. It says that as long as the function and its derivative exist, just first derivative, then the integral is equal to 0. The proof is actually, the rigorous proof is quite complicated. So when I give, no, it's not complicated. It's what is it? Complex, right? So that it requires several steps. So when I teach it in complex analysis here at Berkeley, it takes maybe like 2 or 3 lectures, like to fully prove it, with all the rigor. But you can sort of take my word. You kind of see what's going on, right? So if the function, if there are no singularities, you can kind of move the path a little bit, right? And then you can basically show that that you can do it, right? So this kind of part of the set which you can sort of smear it over. The integral around kind of this path, this little path is equal to 0, which I sort of showed in black arrows. And so in that sense, yes, so kind of you've proven that integral over the small patch is 0 by finding explicit parameterization. You would kind of find it, like, break it into blocks, right? So you say there's a gamma, and then you would sort of dissect it into vertical lanes, right? And then you would dissect it into those, and then you just show that all little integrals over each of those boundaries of each of those sets are equal to 0, provided that the function has a derivative. Now, this is not the miracle of complex analysis. So if you remember, in the real analysis, in order to make pretty much any analytic statement about like a Taylor series or some convergence of some series, you need to have many derivatives. So the function has to have many derivatives. So if you say doing Taylor series, it should be infinitely differentiable, right? Otherwise, you cannot take, say, hundreds derivative. And that has to be sort of put in by the condition. In complex analysis, you only need to know first derivative. So if you know for sure that the first derivative exists, then all derivatives exist automatically. Just like that, yeah. So those functions, but it's a stronger statement. So it's not just derivative at a point, it's derivative in an open subset, right? It's like derivative on a disk or in some open square. So if derivative exists at every point of the set, then all derivative exists. And this theorem is true. And those functions which derivative exists, which are differentiable, are called holomorphic. Holomorphic or complex differentiable. So example of a non-holomorphic function is absolute value of x, absolute value of z divided by z, say z plus 1. This is not holomorphic. So in other words, function is holomorphic if you, so you can sort of ask it differently. So say you have a function of two variables, f of x and y, and then you can sort of use the fact that x is the real part of z and y is the imaginary part of z. You can ask yourself, can you write it as the function of complex variable z? So you can always write it in terms of z and actually, let's say z bar here. So this function g of z is not holomorphic because it depends on the z bar here. So if you have a function of two real variables and you wish to rewrite this function as a function of single complex variable, so it is holomorphic when you write it only as a function of z, not z bar. Does that make sense? Okay, maybe I want to iterate this a bit more, so it's also kind of important. So and then we can talk. It's okay if we don't have time to talk about the homework. Okay, so can just answer questions, right? And then yes, we have that. So example, right? So you have the function x plus y squared. How to write it as a function of z and z bar? So we know that z is equal to x plus iy, z bar is equal to x minus iy, and then you can solve it as a function of, you can solve it for x and y. All right, so let's add together. So you can see that x is equal to z plus z bar over 2, y is equal to z minus z bar over 2i. Right? You can plug it here, plug it in here. So you get z plus z bar over 2 plus z minus z bar squared over 2i. Well, let's calculate what is it equal to. We can open up the parentheses and you'll see that we'll take out 1/2, maybe 1/2 I, this is 1/2. Right, to have z plus z bar, and then 1 over I is, the function 1 divided by I is negative I. So and then it's minus I times what is it, z squared minus 2z bar plus z bar squared. And you can see that it depends on both z and z bar, right? So there is no way to write it only in terms of z. So this function is not holomorphic. However, so yeah, so it's another kind of statement. So f of z. Okay, I'll take this. But now let me give you an example of a holomorphic function. So say you have this x squared plus 2i xy plus y squared. Minus y squared. Okay, which complex function is this? So if z is equal to x plus iy, what is this?
Z squared.
Yep, it's z squared. That's right. It's just z squared. So this polynomial with three monomials is just one complex function. So it does not depend on z bar and does not depend on contrary. So this kind of so yes, you can ask this question: when, so you can say, okay, so okay, this sounds like a very cool theorem. Why didn't I know this before? Why couldn't I use it for any path in say on a real plane? So I'm given a function of two variables x and y, and I want to integrate them over this closed path. Why didn't I know this before? Well, turns out that not every function of two variables can be presented as a holomorphic function. If it can, then it must depend only on z, not on z bar. So in other words, the derivative of this function over z bar should be equal to 0. So it does not depend on z bar. This is sort of condition on the holomorphic function. Yeah. So if f is holomorphic, then it's true. If it's not holomorphic, then all bets are off. Okay, questions? Okay, good. Just to finish on this part, to show that it's a really cool thing. So part one was to show that integral over this thing over the circle was equal to 2 pi I, and then it's equal to 1. Part two is that we can, if function is differentiable, if it's holomorphic, we can move the contour of the path. Now let's combine 1 and 2. All right, so 1 plus 2 suggests the following. So say you have a rather complicated function. Let's just write a rational function for simplicity. So say you have some polynomial of z in the numerator and divided by some, so there are some poles, say z minus a1, z minus a2, z minus a3, where a1 and a3 are just some complex numbers here. So a1, a2, a3, and you want to integrate this f over gamma that goes like this. Some clever loop or whatever. So this is your gamma, and then also the direction is important. So you probably heard that if it goes counterclockwise, then it's a positive sign, right? So if it's clockwise, then it's negative sign. Just need to multiply by a minus sign. But say it's oriented positively. So combination of 1 and 2 suggests the following: is that, well, so let's start with 2. So you can what we just said here. So function. So here, so clearly this function away from those 3 points is differentiable, right? Because we know how to calculate derivatives of rational functions. So if you can write a function, it says holomorphic function is a very simple object, right? It's like if you have a formula f of z equals stuff, then essentially it's there, right? You can differentiate it, and it's clear from the construction where is the domain of definition. So here, so clearly this f is defined everywhere except in these 3 points, right, where it's divergent. Okay, and then well, so away from all these 3 points, we can move the path a little bit. Well, we can essentially move it until we hit those poles, right? You can kind of contract it down, then you can further contract it down, and then sort of when these branches of path pinch, you can sort of cut them off, right? So eventually you can cut them off, and you have 1 point. We could have 3 disjoint disconnected paths, right? 3 disjoint disconnected paths, each of them oriented counterclockwise, possibly to sort of preserve the same orientation. So let's call this with the same notation, right? So it's gamma 3, it's gamma 2, gamma 1. So it's equal to the sum gamma 2, right? And then, in fact, we can deform further those gammas to be unit circles. So each of the gammas locally, like in the vicinity of these points, will look like just the circle of some radius. So yeah, it doesn't have to be unit circles. If you go back to this statement here, so what if the circle is not of a unit radius? what if just going to do a little amendment to part one. So if circle is if not of unit radius, right? So then z will be equal to absolute value of z here, and we need to stick it in here, right? But then when you do the integral, so integral, let me just do only n equals 1. So dz over z, if point is not okay, so if radius of the circle is not equal to 1, right? So absolute value of z is equal to this r, to the radius of the circle. So then dz over z is equal to, and here we also have absolute value of z, right? So it's equal to, question? Eunice? Oh no, I just got unmuted, yeah. Okay. Yeah, so then dc over z is equal to, but you can see that it cancels out, right? So it's equal to I absolute value z e to the I phi divided by absolute value of z e to the I phi, right, d phi. So we see that everything cancels, and the answer is equal to 2 pi I. Okay, so radius of the circle doesn't matter. It doesn't have to be in circle. The answer, so this answer is still true. Okay, and because of that, well, what is the answer equal to? Yes, essentially each of those three integrals will be narrowed down to integral over a small circle around the respective singularity, right? So for example, here you would do a little loop around A1. Here would you do a little loop around A2, and here you'll do a little loop around A3. So what is the answer? Well, so let's consider one of them. Let's do the gamma 1. So integral of gamma 1 of f of z. What is it? So inside the gamma 1, right? Okay, let's factor the formula. So integral of gamma 1 over z minus a1 times, I'm not doing anything, I'm just factoring out the expression. Now, this is, well, dz. Now, this will give us 2 pi I, right? And this function is well defined at z equals to a1. So in fact, it's defined everywhere inside this disk. So which means that the answer is equal to, well, 2 pi I, and instead of z we substitute a1. Right, that's it. So this expression is called the residue of f at a1 and denoted as res a1 f of z. So what is residue? Basically, you factor out the 1 over z part, the sort of the contribution that is singular, that sort of behaves as 1 over z as you approach this point, and then you just plug in the value of a1 into the rest of the function. Does that make sense? Yeah, and then analogously you can write that integral of gamma 2 f of z is equal to 2 pi I times the residue of f at a2, and then the same with 3. Yeah, so the full, let's call it I. So I is equal to 2 pi I times sum of 3 residues. Residues of f at a1 plus residues of f at a2 plus residue of f at a3. Which is some rational function of this form, right? So this is residue 1, and then will be similar answers for 2 and 3. And as you can imagine, there's a generalization. So this is called a Caucus Theorem. So it requires that f is holomorphic or is differentiable. And well, on U without those points A1 through AN, right? And then for every path gamma in U, every closed path, integral of f over gamma is equal to sum I from 1 to n. So it's yeah, it's like it's with 2 pi I, and then here you'll have residues of f at ai, but you also need to multiply them by what is known as winding number. Let me show you what this by an example. So let me give you an example sort of to illustrate why this winding number is important. So say this is set U, right? You have your singularities, your points, your A's, and then say the path goes like this. You wind 2 times here, then you wind in opposite direction 2 times there, and then you kind of come back again here. So say it goes like this. Sorry, no. Need to follow. I start from here. Let's say start from here. I go, yeah, and here I go in the negative direction, right? So if this is A1, A2, A3, and A4, so in this case, winding number for 1 is equal to 2, winding number for 2 is equal to -2, and winding number for 3 and 4, 1. So it will be the answer with coefficient. So it depends on you can, of course, you can wind many times. That will, of course, multiply the answer by the corresponding winding number. Yeah. Now, if in the previous example you would decide to put some power here, which is different from 1, say 3, then the corresponding residue is 0. Because, well, as we see, so in the previous example, integral of 1 over n for n bigger than 1 does not give you anything. Yeah. So see, it looks like magic, right? It does not, well, essentially the whole calculation boils down to calculating those residues. It still can be hard, like when the function is rather complicated, but it's, order of magnitude easier than what the multivariable calculus sort of requires you to do. So yeah, so that's kind of the gist of complex analysis. And essentially, yeah, so like a lot of theorems, well, pretty much in any part of mathematics or even like in physics, statements in physics are proved using this Cauchy theorem. Like often you would need to calculate the integral, but just use the Cauchy theorem to make some estimates, like on the value of the integral to some proof. Okay, yeah, any questions at this point? So we talked about, well, 2 big sort of directions. Yeah, so like you can just do, yeah, there was analysis and partitions, then, but in a sense, you need complex analysis pretty much for everything. It's really kind of very ubiquitous. Yeah, then you can do those combinatorics, and then, yeah, any questions at this point? I mean, of course, like it's a lot to digest. I'm just giving you this tool so you can decide. It will help you to decide what to do next. And I think if you don't like the project, you can, turn it down and take another one. I think that's okay. We should have enough time. So I know we have what 5 more weeks, right? So like within those 5 weeks, we have like meetings every week or something like that, right? And then you need to report me on the progress of what you have written and what you have read and maybe written. Sort of. Yeah, and then sort of the third direction. The big direction will be the well, applications in geometry. And that's partly what I'm working on myself. Geometry and physics. And by physics, I mean string theory. String theory or quantum field theory. So yeah, it's a huge subject. Of course, it's 5 weeks is not enough. Probably 5 years is not enough. But sort of let me give you some ideas. So say you have the following setup. You have some space, some manifold X. You can write it in some blob like this. And then you map curves, either real curves or complex curves, into X, right? So say those say these are Riemann surfaces, right? So say they look like say that they look like spheres. So it's like a two-dimensional sphere, right? And then, well, you construct some functions. You study in some function map of those spheres into a space. So X can be a sphere itself, right? For example, it's a legitimate question to ask how you can map sphere to itself, and what kind of different maps you can have, right? So and turns out that it is non-trivial. So the sphere can wrap itself several times, and these maps can be very complicated. And that's what the topologists study. For example, maps from S2 to S3. So if you wrap a 2-sphere around 3-sphere, 3-dimensional sphere, how does this look like? It's also very complicated. Now, and then, yeah, so basically you need to define this map. So luckily, complex analysis is again of great help because sphere is a complex manifold. And so another detour of the complex analysis. And it has its own name in complex world. It's called CP1. It's the complex projective one-dimensional space. That's why there's one here. So what's the deal here? Well, so let me show you that there's a following, or sometimes it's denoted as C, like with a bar, which is the extended complex plane. Now, here's how it works. So take a sphere. Here is its equator. And then let's kind of continue the equator to a plane. Right? So in other words, you dissect the sphere by a plane along the equator. Right? And then here's the North Pole, and here's the South Pole. So think of Earth like the globe, like it will be very helpful. Now, and then we can draw lines which connect, go from the North Pole through the plane. So it sticks out and then goes inside the sphere, and then it punctures the plane here, right? And then continues on further, and then gets out of the sphere somewhere here, right? So every line that goes down, right, which is not parallel to the plane, will do that, right? It will intersect sphere in 2 points. So let's call this point P and this point Z. What does it show you? It shows that there's a bijection, right? So there's a one-to-one correspondence between the sphere without North Pole and the complex plane. And bijection goes by this geometric picture, right? So it's one-to-one, right? So for every point Z, you can just connect it with the North Pole and see where the intersection with the sphere goes, and you'll get point on the sphere, and vice versa. Yeah. And the same, you can play the same game with the South Pole, right? So S2 minus South Pole is in bijection with C, and then you can show that this bijection is analytically kind of nice, right? So it's if you write explicit formula, which is not so hard, this map is differentiable, and so you can, if you like, you can parameterize it. Like point P has three coordinates in 3-dimensional space, right? And point Z has only coordinates in a 2-dimensional plane. It's very easy to write down the map. In fact, if you decide to go this direction, I think I'll ask you to do it. So yeah, it's of course it's written in all textbooks and stuff. So what does it tell you? That if you take a complex plane and you add 1 point, then you'll get the sphere. By adding, I mean sort of adding it topologically. It's kind of, you would glue this point, kind of, you would take the plane, kind of wrap it up into the sphere with a little hole, and then you just glue a point in there. So that's what this CP1 or sphere is, right? So the CP1 looks like complex plane, and then there's a disjoint union with point, let's call it, well, point N, but I'm going to call it infinity. And you probably can guess why, right? So if you are in a complex plane, right, you have Z, and then what happens if you move Z to away from the origin as far as it goes? But you go to this complex infinity. In complex world, there's only one infinity, right? So unlike in the real line, you can have infinity on the right, like plus infinity and minus infinity. In complex world, there's only one infinity, and also complex numbers cannot be ordered. Like there is no sense of making an order. You cannot say that 7 plus I is greater than 2 plus 3I. The statement doesn't make sense. You can say that 100 is bigger than 10, but once we go to complex numbers, it loses every meaning. So yeah, and then if you think about this map, so the further this line tilts, right? So you want to tilt it further, and then it would, intersect plane somewhere further along the line. So the closer this point P is to the North Pole, the greater will be the absolute value of the point Z on a complex plane. So that's why you can associate in point infinity and complex infinity to the North Pole, and point 0 to the South Pole, sort of in this presentation. I'm sorry. Okay, I will. It's the daycare calling. Okay, we're almost done here, but okay. So I'm just gonna tell her that I'm calling you in 10 minutes. I need to drop my daughter at. Give me 1 second, guys. Where is she? Yeah. So right. So yeah. So this is CP1. So therefore, it's literally, so this North Pole is literally Z goes to infinity as Z approaches to this point, which is actually very nice, right? So it's kind of complex functions can go to infinity, right? For example, function 1 over Z approaches infinity. So, and then you can use this, and now sort of 1 over Z is defined everywhere on the Riemann sphere, right? So 1 over Z is a map from CP1 to itself, right? It maps point infinity to 0 and vice versa. And so it's very convenient. Like there's there's no mystery here. Yeah. Okay, so back to this. Yeah, so basically, sphere is a very nice complex manifold, right? It's the we'll talk about this, and then well, what happens here? So you take those. You would describe this map as a complex function of z here, right? And for example, if you look at polynomial maps, right? So say if z is some polynomial of certain degree, d, right? So polynomial has coefficients, right? And then so polynomial degree d would have well, d plus 1 coefficients, and then you can ask yourself how the properties of this map change as you vary those coefficients, right? So it's ad z to the d, now plus ad d minus 1 z to the d minus 1, plus etc. plus a1 z plus a0, so d plus 1 coefficients. And then, well, you can sort of ask the questions about all of them at the same time, right? So what happens? So each of them can be a complex number on its own. To have a d plus 1 complex dimensional space of parameters. And yeah, so what happens with this map? Like other interesting sort of corners in this parameter space when the map degenerates, like for example, when the sphere kind of pinches off, like into two spheres like this, or maybe more spheres, like when it becomes really elongated, and so on. So to answer those questions, you need to sort of we define M, this moduli space of maps. Moduli space, which is just the parameter space of those variables, and then we set up certain integral of f of what? So integral of something, not of f, of well something over the moduli space. That something can be one or some other sort of class, as we call it. And here this should be, so if it's a moduli space of dimension d, it's some d plus 1 dimensional integral, which you need to regularize somehow and basically understand what it is, define it properly. Yeah, and then, well, turns out that you can do it. And then after a lot of work, this can be represented, at least in this case, as a certain sum over partitions. Over partitions of the, again, of something. So that was provided that there is some action of additional symmetry on the space and so on. So I would say that this is the hardest part and requires most of the new material. Because essentially everything is new here, right? So you've probably heard this part of what is known of branch of mathematics, which is called algebraic geometry. When you understand geometric objects algebraically in terms of polynomial functions. So yeah, I'll send you the notes. You have time to decide and let me know what you guys think. Do you have any like preference after today's discussion? So I know Emily expressed her interest in analysis. What else? What are the other people think? Eunice, what do you think? Do you do more analysis, more combinatorics, or more geometry?
I think analysis is cool.
Analysis is cool. Okay, very good. Kyle, what about you?
I think I would prefer analysis.
I see. Good. Zeo?
Analysis.
Michael?
I'd also prefer analysis.
I see. So you all guys like Andrew, Jairo?
I think the last one was cool, but it sounds,
It sounds pretty complicated. Yeah, no. I just sort of wanted to show you that, to show you how far things can go, and it's still they boil down to partitions, which is actually pretty amazing. Yeah, it's good. So I hope I convinced you that partitions are ubiquitous. They're everywhere. Yeah. Okay, sure. Yeah. So let me think about. Did I ask everybody? I think I asked. Yeah. Okay, so we'll do some analysis. Probably maybe application to combinatorics. How about this? How about So proving those formula with partitions, like some combinatorial formulae using analysis. Does it sound good? Yeah, sure. Yeah, I think that sort of was part of the. Yeah, so essentially, yeah. So the analysis. Yeah, we can. If you like, we can have like overall lecture, like one more like lecture on complex analysis with all of you. So since you all need it, we can. Yeah, so let me. Yeah, let's figure it out over the email. But I think since we all need complex analysis, we can just all have another lecture on that. So yeah, or I can just post some pre-recorded videos and we can go from here. Okay, good. Yeah. So and then feel free to ask me questions, or like if you have more specific preferences, it's like what, more specifically, what do you want to do? Also let me know. I'll start looking for projects for you. Like basically, we'll start with some reference, like a book or paper. So maybe a textbook in complex analysis, and we'll go from there. Okay. Okay. Thank you, guys. We'll see you next time. Thank you, guys. Bye.
Bye.
Thank you.
Thank you.
Thank you.
Yeah.
Thank you. Bye.